area was taught to you in 130 if you took 130, and it was also taught to you in 151. Okay? In theory, as you move from 130 to 151, it should have scaled in difficulty and become more in-depth. 130 should have been a very basic level. 151 should have been more in-depth. 152, you entirely ignore it, and then you move into OChem, where you're expected to know a lot of these principles so that we can now stack even more on top of it. Okay? Just real quickly, show of hands. We throw on the brackets. How many people got something, single bonds, all those electrons, -2, all of that? Right? That's what you ended with, right? Okay. That was about half the class. Did anybody look at Google? No? Okay, well, that's interesting. You're like, don't trust Google. Good. Good. It can be questionable. You go to Google, Google's not going to tell you that answer. Okay? And in fact, if you put that on as a Lewis structure, for most chemists, they will tell you are wrong. Okay? That is not a proper Lewis structure. And yet half of the class thinks that's correct. Okay? All of OChem is based off of Lewis structure. Half of the class is coming in with the wrong philosophy to Lewis structure. This is a big freaking issue. Okay? Some of this has to do with Gen Chem, some as a field. Some of it has to do with Gen Chem instructors. Some of it has to do with you as a student. Okay? So there's a bunch of complicating factors that screw up Lewis structure. This is why I have a Lewis structure video that is painfully long at an hour. I sort of apologize, except half of the class got this wrong. Okay? So it is clearly something that needs to be reviewed. Okay? The video that I give you to watch on Lewis structure is geared to Chem 130. Okay? So fundamental chemistry. Right? There is a section in it that scaffolds up to higher levels for 151 and sort of touches on the aspect of what we would need for OChem. Okay? But we need those basics first, because those basics are what we use to do everything else. So for most OChem courses, the homework in this chapter is to do hundreds of Lewis structures. Okay? You're going to do tons of Lewis structures. Okay? And the intent behind that homework is to get you comfortable with the approximations, okay, the simplifications that we do within OChem to ensure that you get the correct structure. Okay? So if you're like, I need that practice, there you go. There's your number. Hundreds of Lewis structures. Well, let's say 30. Okay? Find 30 simple Lewis structures. Pull up a Chem 130 textbook, pull up your Gen Chem textbook, and do those. Okay? So, how do we go about doing this? Okay? The why we do things becomes really, really critical. Not just that I get to this answer. Because what this Lewis structure shows is where all the electrons are located. That allows me to predict how those electrons can move. That's OChem. If your structure is wrong, it doesn't matter if you know how to move electrons. Nothing you're going to do afterwards is correct. Okay? So you need to be a little bit more confident in Lewis structure. Okay, so, and I just shuffled a whole bunch of stuff around, which is irritating for me now. Okay? How do we draw Lewis structures? This is the rules. Okay? These rules are slightly different in every class in general chemistry. But these work. Okay? These rules are better than any rule I've ever seen in any textbook online anywhere else. They are so freaking good that if you go into the tutoring center, that's what you see for the rules on their Lewis structure handout. I also wrote that. Okay? There are places that vary and encounter slight issues, and you can run into exceptions. Typically, the colors are pulling things out. Okay? The exact order isn't super necessary for probably the first 2 steps, but then everything else, the order is really important. And that order really comes in when we're dealing with Non-bonding pairs of electrons that can be placed in multiple locations. That's where we get the idea of resonance. In second semester, if you're asked why, all you need to do is write resonance. Okay? Might be a little cocky and overstated, but it's probably right. Okay? And it's right enough that anybody grading is going to be like, are you just throwing crap on the paper and hoping I give you points? Or do you actually know? Okay? So it usually means you get it right. Okay? The last step on here is assigning formal charges per atom. That formal charge per atom is what's going to dictate some of the extra steps that you should have learned in Gen Chem that we also kind of don't need to worry about in OChem. Okay? For instance, when we go back and look at our sulfate, we've got the one structure drawn on the left. Google will show you something more along these lines, okay, with the double bonds. Okay? Anybody, particularly for those of you that said the structure on the left was correct, see an issue with the structure on the right? I did the left, right? Yeah. Yeah, what's your issue? What do you not like about the structure on the right?
It's supposed to be an octet, but...
Okay. All our atoms are supposed to achieve an octet. They're supposed to have 8 electrons around them. Okay, so let's get through on counting. Okay. Counting is a whole nother issue, okay, that we also need to be careful with. Because I will get students telling me the amount of electrons around sulfur are 1, 2, 3, 4, 5, 6. No. What is a line?
2.
A line is a bond that's made up of 2 electrons. Those 2 electrons are shared, which means sulfur has access to not 6 electrons, but 12. It has definitely exceeded the octet. Okay? Why should I be able to exceed the octet? Sulfur's in a d orbital. Has access to the d orbitals because it's in the 3rd row. Yes. Okay? That explains why sulfur was able to. Why did sulfur exceed the octet? I heard to balance out the 0. I liked the first part. I didn't know what the 0 was. And then I heard back here following up. Reduce formal charges. What formal charges? So some people are like, oh, the one's on sulfur. And I see a couple people looking at it being like, kind of laughing along with me, like, what idiots? There's no charge written up there. That's the problem. Those charges need to get specified. Okay? You have to specify charge. You don't get a choice. So how do we calculate charge? Okay? So I heard valence electrons minus non-bonding, and that was exactly what I was hoping to hear. I heard somebody say the sum non-bonding plus, okay, usually it's written plus the half of the bonding electrons. Gen Chem tells you this rule, and why? The rule of Gen Chem is very simple. Units. The units in all 3 of those expressions are electrons. That's why that formula works. Okay? You're bringing in a sum of. Why? Because it looks fancy. Irrelevant. So I'm going to change that. I don't want a sum of, because what will end up happening is then I just add everything up. Valence electrons minus non-bonding electrons. That didn't change anything. Minus bonds. Therein lies the problem with this method. What is the unit in that last term? Bonds, not electrons. Oh, you can't do that subtraction. They're different units. We're not in Gen Chem anymore. We can make up crap as much as we want. Okay? Get rid of the fraction. Get rid of the sum of. We just do it. It's lovely. So when I look at, say, this oxygen, oxygen comes in with how many valence electrons? 6. How many non-bonding electrons are around it? 6. Okay, which becomes a fun one too. With the non-bonding electrons, sometimes you'll also see non-bonding pairs of electrons. Well, do you mean 3? Because there's 3 pairs? Or do you mean 6 non-bonding electrons? Yeah, get rid of the pairs. Non-bonding electrons. Okay, so there are 6 non-bonding electrons. How many bonds does it have? 1. I know I said there were no numbers. Hopefully these numbers are okay. 6 minus 1, we get -1. The charge on that oxygen is a -1. How about the next oxygen? 6 minus 1. For those of you doing longhand, those of you being like, isn't it the same? Yes. -1. Next oxygen. -1. Last oxygen. -1. So the charge on our sulfate is? Wait, +2. I said the charge on sulfate is? Sulfate is SO4. -2. What's the charge on sulfate? -2. Answer the question that's asked, not the question you want to answer. What is the charge we've now shown? -4. Is that right? No. What does that mean? Sulfur has to have a charge. Conveniently, we've not identified it yet. So let's take a look at the sulfur. What's the charge on the sulfur? For those of you being like +2, knock it off, do the math. 6 minus non-bonding, if we go in the sequence, would be 0 minus 4, and we get a +2. There's a lot of work there. Can I delete a bunch of it? That was not a very confident yes. You want me to leave it?
You can erase it.
I can erase it. Thank you. I didn't want to look at it all. Numbers are confusing, right? Let's clean it up. Is there a lot of charge in that structure? Yes. That's ugly. That's awful. If we go through and do the exact same approach on our other structure, what do we find? The oxygens on the horizontal axis, for lack of a better descriptor, are -1. Anything else? Nope, that's it. Which of those two structures looks prettier? The second one. Which one should you draw? The second one. Why should we draw the second one? It's prettier. Yeah, good catch. Okay. Most of what we do in OChem is make it look pretty. Okay. There are some other rules that go along with that. Okay. When we're looking at our Lewis structures and we want to rank best ones, the first thing we need to do is satisfy the octet. Okay. That is where you should have ended 130. Yes. Satisfying octet. 151, you should have been minimizing charge, which means 151 does not get the big ugly one with all the charge. 151 gets the double charge, double bonds. Okay? There are all sorts of other weird reasons that people come up with, say, oh, you can have double bonds. They're nonsense. This is how it works. Okay? We are minimizing charge. How did we minimize that charge? By making a double bond. How did I make a double bond? I moved electrons. Which electrons did I move? The oxygen. Just because I can. If I told you to move the electrons on the oxygen on a test, how many of you think you'd get it right? Okay. Which oxygen?
Sure. Are you trying to do the top one?
I didn't ask that. I said move the electrons from the oxygen.
Gotcha.
Okay. So we've got an awesome volunteer. Thank you for that, saying we took these electrons and we moved them into there. You are wrong, sir. I wanted you to move these electrons. And you're like, you didn't ask a good question. You also didn't defend that there were multiple options. That's resonance. That's why resonance is tricky. Because there's multiple options, you have to be very specific in which electrons are being moved. If you're being asked to draw the Lewis structure for sulfate, the structure on the right is also wrong. Okay? Because that structure happens to represent only one of the possible ways we could have arranged those electrons. Because I could have just as easily, and I'm not going to draw all the electrons, done it that way, right? Okay. So now am I right if I draw both of those? But now, right?
No.
Okay. When we're talking resonance, you have to draw all. So a Lewis structure question can go from a relatively simple, oh, I just draw it out, there it is, to now I have to draw 5, 6, 10 different structures. Okay? When we're being asked to draw Lewis structures, what's happening is in this best categorization. We decide, when we look at these, that neither one of those is better than the other. Why? We've satisfied octets, we've minimized charge. So there's nothing that allows me to distinguish between these, which means they're all correct, which means I must draw all of them. If there are cases where there's multiple ways I could place those electrons, but those rules differ, now I can say, well, I don't have to draw that resonance structure because it's not as good as this one. It's a challenging thought. Probably want an example on it. We will see one. Okay? So, Lewis structure, to start, we need the same fundamentals to begin with. Those same fundamentals, not that direction, are here. That's where we're starting the conversation. Okay? For those of you who think that these rules don't work, I have never encountered an exception. Never. Okay? And I've had people intentionally try to break them. Okay? They work phenomenally well. Okay? When we get to OChem, we have to build beyond that because our structures get more complicated. Okay? In that, what ends up happening is we make a bunch of simplifications. We already talked about some. Our periodic table, hydrogen, boron, carbon, nitrogen, oxygen, and our halogens. I didn't want to list all of them out. That's our periodic table. Okay? We will get simplified shapes and hybridizations, which we haven't talked about yet. And then when we get to Lewis structure, we're going to make a crap ton of abbreviations. Okay? So I want you to be aware of these abbreviations as we move through, because we're going to be constantly using these. And it's how your smart work is done, it's how paper homework is done, it's how exams are done. So when you watch someone studying OChem and they're drawing weird hexagons and structures, there's a lot of implied information in there that you are required to know is behind the structure. So watch out for those secondary rules. Okay? So, formal charge. We've got, sorry, did you want a picture of that? I just saw the camera. It is in the slides. It's later in the slides, though. I copied it and dropped it earlier because it was important enough. Formal charge. Valence electrons minus non-bonding minus bonds. Keep it simple. Okay? If you change the arrangement of your bonds, the formal charge will change. Okay? So that can have pretty drastic impacts on how we interpret our structures. Okay? Oxidation state, or oxidation number, on the other hand, won't change with a change in the Lewis structure. Okay? Because the oxidation state is more specific to an individual atom, and when we change resonance things, we aren't changing the characteristics of that atom. We're just changing where we're drawing the electrons. Okay? So oxidation state, while more consistent for any given structure, is also a little bit trickier to interpret. In fact, I'm not sure that I provided the correct formula there. Okay? And it becomes a lot more difficult to use when looking at a structure. So when we draw out our structures, we specify formal charge, not oxidation state. And that is largely by convention. We've just decided that it was easier for us to do formal charge. Now, because somebody made that decision, everybody follows it. Okay? So we can see oxidation state pop up, and we can use oxidation state rules to figure out if a reaction was oxidized or reduced. You remember that, right? Yeah, that was fun stuff. Okay? OChem can also dodge all of those rules too. We don't have to quantify out that way. Okay? So, some Lewis examples. I meant to cut up some papers, so we won't do that. Okay? Because I didn't do that. You guys want to take a look at C3H8 on your own, or do you want to look at some examples first? Examples first. Okay? So let's walk through the very first one. If you've seen the Lewis structure video, this is a repeat. I apologize. If you haven't seen it yet, it will be a repeat when you watch it. What's our first rule? Valence electrons. Carbon has 4. I heard a times. We're just doing CO2. It's okay. Oxygen, 6 times 2. For those of you that might be like, whoa, where did those numbers come from? The column name, just in case you didn't remember that. So for carbon, the column name is Roman numerals. Look, the column Roman numeral name is 4. Anything in that column has 4. For oxygen, Roman numeral 6. Anything in that column has 6 valence. Okay, so the periodic table has a lot of that encoded. You will probably memorize it and not need the periodic table, but we'll address that later if we get there. So, total valence, I now add everything up and do the little multiplier first, right? And get, that would be 12. And 4, 16. 16 valence electrons. Next step, I want a central atom. The central atom is typically the least electronegative atom. We had a good question over on the side of the classroom. Why should it be the least electronegative atom? Well, what is electronegativity? For those of you that had the conversation on the left, don't answer. What is electronegativity? The ability to attract, and this is where we get a lot of people, electrons. No, that is actually not the definition of electronegativity. That would be the definition for electron affinity. What is the definition for electronegativity? Losing electrons. You're like, it wasn't gaining, it must be losing. That would be the definition for ionization energy. What is the definition for electronegativity? The ability to gain, yes, or attract. Electrons is there, but there's a very important word that has to show up first. Bonding electrons. If I have an individual atom sitting on its own, I'm not using electronegativity to evaluate anything about it. I have to actually have that bond. Once I have that bond, I can now use that to explain where the bonding electrons are going, be it towards one atom or the other. Okay? Why would the least electronegative be in the middle? Well, I've got 2 atoms to choose from. Okay? The most electronegative or the least electronegative? Which one do I want to put in the middle? Okay, we said least. So, devil's advocate, let's put the most. The atom in the middle is going to have how many bonds? Lots or little? Probably lots. It's in the middle, right? The atom on the outside will have fewer. Okay, if I put the most electronegative in the middle, it's going to have the most bonds. What was the definition of electronegativity? Attracting, bonding electrons. So just using the definition of electronegativity, how many bonds would I expect on a more electronegative versus a less electronegative? The more electronegative should have fewer bonds than the less. Okay? Are there exceptions? Yeah, there's always exceptions. Okay? But those exceptions tend to follow other patterns, like Hydrogen is less electronegative than oxygen, but when I build water, oxygen's in the middle. Why do I do that? I'm not sure I would go with molecular shape. Hydrogen can't physically have two bonds because it can only hold two electrons because, sort of except S shell, because magnesium also is S shell, but it could get two bonds. Why does it only have two electrons? There it is. First row has how many electrons? 2. That's why. There's literally only space to put 2 electrons around hydrogen. To put more electrons around hydrogen, you'd have to jump up to the second energy level. That's too large of a jump. This is why we have the octet rule when we look at the second row. When we jump to the third row, now all of a sudden we can expand the octet. Why? The jump from the 3p to the 3d is a tiny jump. That's why I can expand the octet. Every other place, it's a huge jump. That's why we can't expand. So hydrogen can only have 2 electrons around it. By definition, if I put hydrogen in the middle, I've exceeded its capacity to bond. Neat. It's helpful if you maintain the eraser. Okay, so center atom should be carbon. So we'll scatter the oxygens around on the outside. So there we go, they're on the outside. How many of you want to do? And you're laughing. Be careful at what you laugh at, because you will probably draw that on the exam. Okay? Why would you be laughing at that? It's not right. Why is it not right? What have you got? Yes, you would be right. Oxygen would be the central atom, which would defeat the purpose of carbon being the central atom. Good call. That was really dumb. My bad. You'll still do that. And then we can point to rule 1, and we didn't even have to dig any deeper than that. Or rule 2. Okay? So, carbon's the central atom, oxygen, oxygen. Now what do we do? Add electrons. Where do I want to add electrons? Most electronegative. So I'm going to place the electrons where? On the oxygen. How many of you were actually trained to place electrons onto the oxygen and not onto the carbon? Take a look at the hands. Less than half of the class. Okay? This is why it's so important to make sure we're on the same playing field. Okay? So we'll go on the oxygen first. Ideally, we would actually place that first pair here, because I know I want a bond eventually with that carbon, so it makes the most sense to go there. Okay, how many electrons? That would be 8, so what do I need? I got 16 total, I got to place the other 8. Where am I going to place those? The other oxygen. Now what do we do? Create bonds. Okay, really the bonds were already created, but we are changing the notation of what we're drawing to draw attention to the fact that that's a bond and not a non-bonding pair. So for those of you, I think I saw a few people that were trained along these lines. It is a bad training system. What is non-bonding versus bonding? You drew everything as a line. You've made it more confusing. Okay? So now what do we do? Okay, I'm hearing some charge. Charge is 7. Satisfy octet by moving pairs into bonds. Okay? Have I checked octets yet? No, check octets. Carbon has 4. How many is it supposed to have? 8. What do? We make a double bond. So I just do double bond, and now it's got 8. Okay? We have to recognize how we're doing it. By just drawing that line, I've now jumped to 18 electrons. I can't change the number of electrons. So what I'm going to do is take that pair of electrons and move it into the space in between. So really what I'm telling you to do, if we're going to painstakingly do this, is to actually do this. But now I've got a pair of electrons between atoms, and now what can I do? Now I can make a bond. Okay? Why? I really want you to recognize the value that a line represents a pair of electrons. It seems silly. You will screw it up again and again. Okay? So now what? Okay? Carbon still doesn't have an octet, so what do we need to do? We need to move another pair of electrons. What do you mean? Why do I got to go to the other side of the carbon? Why do I got to go to the other side of carbon? What's the octet? Octet satisfied in mine? Some people are like, no. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Octet satisfied. What formal charges?
The oxygen.
So that's cool. You are propagating out into that last step. Perhaps because your background provided you that knowledge that you need to be doing formal charge as a last step. Okay? I haven't looked at your work, but I'm going to bet you didn't actually write down the calculations for formal charge either, did you? Okay? You're right, so that's good. Okay? And if we look at the structure I drew, negative, positive. That Lewis structure, in comparison to the one you guys were suggesting to me, is not the best Lewis structure. Why? More formal charge. Does that make it not a Lewis structure? No. Is it still a valid Lewis structure? Yeah. If I asked you to provide resonance structures for CO2, should you draw that one? Ooh, that's a challenging one. Okay? Very arguably, no. The reason being, they have to be the same energy to count as valid resonance structures. Okay? So you shouldn't be pushing out to that level. Okay? Does that make sense? Should you be aware of it? Yes. And there are bigger cases that we're going to need to watch out for that you need to be extra aware of those circumstances. Okay? So instead of looking at that last example, that's not the pen I wanted. Give me CHO plus. All we did was add an atom, got rid of an atom, and added a charge. Or simple Lewis structure. We can go through and make lines. We get bonds. Okay. Then we go through, satisfy octets. Carbon's missing its octet, so we would have to erase a pair of electrons to make the double bond. Carbon is still missing its octet, so we erase that to make the triple bond. A couple people drew this, and they were like, you told me that was wrong. It is. Bracket width on the charge on it will satisfy me for, say, Chem 130. This isn't Chem 130. You need to do better than that. Your formal charge gets specified where? On the atom. You have to be very specific with that referencing, which is actually going to bring up the next issue with this structure. We're placing what charge on oxygen? A positive charge. What can you tell me about oxygen? The second most electronegative element on the periodic table, which means, what does it want? Electrons. What does it not want? Positive charge. Is this structure the best structure I could draw? Okay, what do you want to draw? Oxygen doesn't want to be positive, right? So what is it going to do? Take electrons. Where can it get electrons from? There's really only two places that there's electrons, right? In the bond with carbon or the bond with hydrogen. Can it pull the electrons from the bond with hydrogen? No, those electrons are too far away, which means it's got to get the electrons from the bond with carbon. So I'm going to take a pair of those electrons, I'm going to put them back on the oxygen. Notice I'm actually using curved arrows, and I'm going to introduce this concept of resonance arrows. Resonance being the double-headed arrow. If anybody thought that that was an equilibrium arrow, you can yell at your Gen Chem instructor, because that is a load of crap. That is not equilibrium, that is resonance. Okay, and it is, I can yell at Brian. I even showed him how to, Wingdings 3 is the proper font system, and I believe it is a capital D. What would the charge be on the oxygen now? Neutral. Fan-flippin-tastic. Except, now the carbon is positive, right? Which structure is the correct structure? Both. If we're saying both, they have equal energy. So it is equally likely to find a positive charge on carbon as it is on oxygen. No, so they don't have equal energy. So it can't be both. Which one's the best Lewis structure? Both was a good catch, because usually I throw that in as a jerk maneuver. Which one's the best? Left, right? Getting a lot of people saying the right one. The right one's got to be right, right? No. Because the carbon doesn't have an octet. The rule is satisfy octets first. So the blue one is the best Lewis structure. This is where resonance becomes fun in OChem. The best Lewis structure is also typically the most useless. It is best making it the most stable. The more stable you are you more likely to react? No. So if I'm going to do organic chemistry, I'm concerned about reactivity. The best may be what I'm expected to draw, but what I need to think about when this compound reacts is not the best structure, but the most useful. And it isn't the worst, because there are a lot worse structures you could draw. Okay? My reference for the most useful is typically the best worst structure, or the second best structure. The useful structure is incredibly valuable to us, and it's going to help us predict where chemistry is going to react. So if I look at the best structure, what might I think is the reactive atom? Oxygen, because it's charged. That oxygen doesn't react. The carbon does. Why does the carbon? Because the oxygen steals the electrons away from the carbon, generating the most useful structure. That's where my reaction occurs. Okay? So when we go through Lewis structures, you've got all these different moving pieces that you've got to watch out for and you've got to consider. Okay? To that end, because I have talked way too long, and somebody else already kind of pushed this with C3H8O. Try and draw out a Lewis structure of that. We'll pick up there next Wednesday, and then I'm going to try and kick it into high gear because I've been going way too slow. Okay? And we're going to take a look at that, and we will prove why you are wrong.